My name is Josh Gargan, and this is my presentation on lines of charge. We have already seen how charged particles interact with other charged particles and neutral objects, but most charged objects we experience in our daily lives are made up of billions of these charged particles. If we assume that a charged object has a uniform density of charge, meaning the charge is spread evenly across its surface, we can determine the field this object generates, as well as how much charge each charged particle contributes. The physics behind uniform density follows the same rules we have seen already. What we must understand about a uniformly charged object is that it is made up of infinitely many charged particles, and each one contributes a tiny portion to the overall electric field. Knowing this, we can calculate the tiny electric field, dE, generated by the tiny charged particle, dQ. dQ is determined based on the object's size and shape, but in this case, that object is a rod of length L. From here, we can integrate over the length of the rod to determine the overall electric field. Once the tape was charged, I noticed that it was attracted to my hands. I also noticed that when two charged tapes were brought close together, they repelled each other, and the charged tape was attracted to neutral objects. It is known that if a plastic pen is charged, it becomes negatively charged. Therefore, if the charged tape was positive, the two objects should be attracted, and vice versa if the tape was negative. The charged tape was attracted to the pen, so the tape must have been positively charged. Once the lab began, I noticed that as I brought the bottom tape closer to the upper tape moved upwards as if it were floating. At the point when the upper tape began to move up a distance of about 0.02136 meters, the tape was experiencing a zero net force due to the electric force from the bottom tape and the force of gravity. The given knowledge that 1 meter equals 1 gram for clear tape was used to determine the mass, which was about 1.5 times 10 to the negative 4th kilograms, and thus the gravitational force of the tape. For this lab, I assumed that there was negligible air resistance and that the charge was evenly distributed on the surface. I start off my code by establishing the known constants, calculating the mass for the 15 centimeter tape, and determining the force of gravity on the upper tape. I then create a function that can determine the dE for each dQ. The lines of charge are made and are based on the number of dQs in each line of charge. The next lines of code establish the dQs for the top tape and calculate their electric field and electric force contributions to the total electric field and electric force. The last few lines of code create the electric force and force of gravity arrows and print the magnitudes of the electric and gravitational forces and the charge on a piece of tape. As seen by the simulation, each tape is made up of 10 charged particles, and each particle on the top tape contributes a tiny electric field as seen by the blue arrows. By treating our observation location as the center line that bisects these two tapes, we can see the sum of all of the particles' electric fields will point in the positive y direction. This makes sense because each particle in this case has a value of 2.037 times 10 to the negative 8th coulombs, so each electric field would be pointing outwards from the charge. This also means that our electric force should point in the same direction as the net electric field. If each tape was modeled as a single point charge instead of a line of charge, then the calculated charge on a single piece of tape would be based solely off the contribution that charge's electric field has on the overall net electric field. Because the tape acts as a rod of uniform charge density in our lab, calculating the charge on the tape wouldn't be accurate by treating the tape as a point charge. The value for the charge on a piece of tape is most likely to be closer to the charge depicted on the right-hand side, because dividing up the tape into more charges means there are more charged particles acting in the system, as would have been the case in the experiment. Our value of Q would get more accurate if we were to increase the number of charged particles to a much larger value, or to take a limit as the number of particles went to infinity. Thanks for watching.